add it to the other. So just so you know, I haven't given you every single slide I'm about to show. Shocker, I know. Boo. But I've done something a little bit different with this one. As I've done in the past with questions at the end, I'm not doing questions at the end. I'm doing questions during. So if you see something that I didn't share, and those that don't have the slides in front of you, so you don't know what I posted or what I didn't post, somebody let me know, because I don't remember. But if it's a question, and I didn't put it on the slideshow, you may want to snap a picture of it just for your own personal collection. Okay? But I'll try to remember, and it's obviously questions that I didn't. What's that? Yeah, I told you you're going to be sick of it at the end of the program. And which class was this? I don't even remember anymore. Yeah, for the photos that are all over your phones, yeah, save them and then dump them, because again, I'll take up your whole memory there with just pictures of my questions, right?
What about video?
Yeah. Good luck finding storage space for all that, right?
Thank God I pay for extra.
All right, so let's talk about this. All right, so this chapter is all on ventilation. This is just part 1 of a 2-part section here that I'm going to do for chapter number 4. But it's on ventilation. So definition for ventilation: the process of moving each breath, meaning the tidal volume, into and out of the lungs. Questions?
Yes.
Okay, that's it. That's this chapter. Ventilation, period. All right, so when we take our tidal volume breath, when we take that normal breath, that fresh air that I'm bringing from the outside does mix in and replaces some of the air that's already in our lungs. So it kind of this constant cycle of, and again, it's not all of it that it replaces, but some of it gets replaced. However, that tidal volume you just took, 500 mLs, let's just say, that tidal volume you just took, did all 500 mLs actually get down to your alveoli to participate in gas exchange, meaning exchanging oxygen and carbon dioxide? No, it doesn't. Right? Good chunk of it does, but not all of it. And we call that what? That dead space. We all have our own anatomical dead space. Now in time we'll get to throwing some numbers to it as far as what mine with your anatomical dead space is. But we're going to get to that, not today, but in the future. How we breathe, the depth, meaning maybe for tidal volume's sake, a little bit bigger volume, and or the frequency, how frequently we breathe, our respiratory rate, if you will, can greatly affect gas exchange. So instead of taking a 500 ml breath, I take in a 600 ml breath. Instead of breathing 10 times a minute, I breathe 12 times a minute. I'm putting more air into my lungs. Okay, so I can alter how I ventilate by simply changing the volume of air I pull in, or how frequently I breathe, or how frequently I pull that air in. Now, the chapter does go into some stuff we've talked about from chapter 6 in the fundamentals class. So hopefully all of what I'm about to share is just a recapture, rehash, because we haven't tested on it yet in fundamentals either. So this part we have mentioned before, talking about Dalton's law of partial pressure, meaning the air in our atmosphere, the air that we're breathing in, contains approximately, what, 79%, 78%, 79% nitrogen, with 21% oxygen and a few other little gases there, right? And we know when you add all those gases up, they're going to equal the barometric pressure of whatever environment we're in. We can say 760 here because we're pretty much at sea level. But that number could be different if we were in a higher elevation city or state. Again, adding those parts and pieces of all the gases in our atmosphere, they should equal barometric pressure. Again, if we're saying at sea level, that's where that 760 millimeter of mercury number comes from. That's what Dalton's law states. So we did this the other day, at least the first one, that if it's you and I and 21% of the air that we're breathing in is oxygen. 21%, and yes, I did round that up to 21%. You can see why, we're almost there. And I determined, well, of that 760 sea level total number, that 760 millimeters of mercury, how much of that is oxygen? We know, well, 21% of it is oxygen. And that's where we got that that number 159.6, and I'm perfectly fine with you rounding up and calling that 160. 160 millimeters of mercury. Anybody want to ask a question? How would you want me to refer to it on a test question? Would you want me to say 159.6, or would you prefer me to say 160?
160.
160? Okay. Nobody else said anything. I'm guessing 160 must be the number. I will make sure it's 160.
I'm gonna remember whatever one you say it is.
How will you put both?
Can't put both. That would be too much of a giveaway.
Just don't put 159.6 and 160 on this.
One question's 159.6, the other one's 160. I'll make sure it's 160. Okay, I'm gonna make sure it's 160. I gotta write that down to make sure when I write the test that I do remember that. We'll round up, call it 160. If we think about nitrogen, if we did the same thing with nitrogen, saying, okay, about 78% of the atmosphere is nitrogen, 78% of that 760 number, then 593, sounds good. I'll take it. 593 millimeters of mercury is the nitrogen. If I said, and everything else, I mean, if you add these two numbers together, 160 and 593,
753.
we're right there sniffing that 760 number. The remaining is the trace gases, argon, helium, methane, these little trace elements of gases, which obviously I didn't put on here because, not that it's not important, but I don't find it important for us to have to worry about doing math with an amount so small. All right, so this was a picture, actually appeared in the cardiopulmonary book and does appear, for this class, and does appear in the Egan's Fundamentals book. The same thing, saying, okay, we take all those parts and pieces and add them together, that's where the barometric pressure number is coming from, that's 760. Everybody okay with that? That was all review from chapter 6 in Fundamentals. Now let's add this part to it. So when we inspire air, so let me step back before I get into this. How much oxygen is in our room right now in millimeters of mercury?
160.
Yeah, that number I wrote down, 160. That's what's in the room right now. If you tell me 21%, I'm going to say yes, but it's 21% of what? Barometric pressure, which equals 160. That's the amount of oxygen in the room. Okay. So when we breathe in, when we inspire, what does our body do normally with that air that we're breathing in? It has to humidify it. At normal body temperature, it should saturate, again, assuming normal, that's us, it's going to be 100% saturated. Okay? 100% saturated. Now, the water vapor pressure at that point is, oh, here it is. Sorry, I'm like, what's my number? Is 47 millimeters of mercury. Now, we talked about 47 number the other day, not to be confused with the 44 number, right? What was that 44 number, milligrams per liter? That was the the water vapor content, physical amount of moisture. This is water vapor pressure, 47. And trust me, and you're not alone if you're like, oh, my head's spinning right now. People get those numbers backwards all the time. 44, physical amount. 47 is what that water vapor pressure is. And I understand the confusion. It's all dealing with water in the atmosphere, right? One's pressure, one's an amount. The 44 number is an amount. This milligrams per liter, an amount. The 47 is water vapor pressure. Water vapor pressure. And you know me on a test, right? I'm going to ask you both of them, or I'm going to ask a question, and both 47 and both 44 are going to appear as available answers. And if your class is like any typical class I've had, I get about 60% of the people getting the answer right, and it's a good number, 40% getting it wrong. Picking the opposite one, 44 or 47. And so when I throw in the other numbers are meaningless, but you're stuck, and it turns into a 50-50. And I see you back there wanting to flip a coin because it's a random guess. Amount, milligrams per liter, is 44. 47 represents pressure, millimeters of mercury. All right, so when we inspire, that air that we're breathing in and the gases that we're breathing in, our body's going to do what? It's going to heat and humidify that gas. It's going to humidify it at what pressure? 47. So, at sea level, the total pressure of all gases in the lung, including water vapor, is going to equal 760. I didn't say in the atmosphere, I said in the lung. Okay? So that 160 we're breathing in right now, because that's what's out here in the room, we pull it in, what is our body going to have to do with it? It's going to have to heat and humidify it. So that 47 number is going to have to take up some of this space. All right, it's going to take up some of that space by the time it's in our lungs, by the time that we breathe it in, because our body's going to heat and humidify. So water vapor pressure must first be subtracted from the barometric pressure. That's what the 760 number represents, barometric pressure. It's going to have to be subtracted from barometric pressure to calculate the partial pressure of oxygen, no more in the room, not in the atmosphere, but actually in our lungs, or what actually gets into our bloodstream, which is what we're getting to the point of seeing oxygen here, into the airways, into the lungs, then getting into our bloodstream. Okay, that's what we're kind of working our way toward. Last week was talking about oxygen in the room, in the atmosphere. This week, we're talking about oxygen getting to the lung. Okay, so first thing I'm going to have to do, that 760 number, first step, I'm going to have to subtract water vapor pressure from it first. And I'll be left with 713 now. Okay, so what does this matter? What's the big deal about this? Here's my follow-up question. Yeah, question, so you may want to take a picture of it. Ring, ring, ring. So how much oxygen in millimeters of mercury is in our airways? All right, in our airways. What I shared before, that 160 number is what's in the room, right? My follow-up question, of that oxygen in the room, how much of it actually got into our airways? Again, trying to signify getting into the lung, right? So, everybody write that down or snap a picture of my question there. Okay, so let's solve it. This is what the answer is going to be if we talk about oxygen in the atmosphere, right? That's our 160 number. I didn't know we were going to pick 160 today, so it's still 159.6, but I'm rounding up to 160. But by the time it gets into our airways, what did I have to do here? I had to subtract water vapor pressure from that 760. So now, how much air or how much oxygen is in our airways, since it's humidified? So 21% of, not 760, but of 713 comes out to be 149.73. I'm going to make the assumption. Are we okay calling out 150?
Yes.
Okay. And yes, both answers will appear on the test. You got to figure out which one's the right answer.
What's the TMC gonna put on the test?
150, 160. They're not gonna ask this question. They're gonna carry it much further. We're just still found it. Yeah, great, fantastic. I barely got this, let alone you're gonna take it further. It'll be okay. It'll make sense when we get to that point, right? All right. So make sure. Did I give you the slide? Did I answer? Did I give you the answers? Okay. Make sure you fill in the answer so you don't understand where those numbers are coming from. So when my question is this, and be very careful when I ask the question. Read everything. Read every word. When I say, how much oxygen in millimeters of mercury is in our atmosphere, that's the 160 number. When I say, well, what about instead of atmosphere or in the room, what about our airways? That's where you're going to give me the 150 number, 149.73. Because by the time that oxygen gets into our airway, into our alveoli, it's being humidified, correct? That water vapor pressure, that 47 number has to take up residence. It has to take a spot somewhere. And so that's why we subtract the barometric pressure from 47 from the barometric pressure. And so we're left with 713. And so 21%, so 21% of 713 is where we got the 149.73 number. Is everybody okay? No? Okay. What do we need to talk about? In the room, where the barometric pressure is 760, how much oxygen is here? Well, it's 21%, but it's 21% of what? 760. That's why I say in the atmosphere, dry. The body hasn't had an opportunity to humidify. By the time we inspire that oxygen, by the time we inspire, you and I inspire that 160, because our body's going to do what? It's going to add moisture to our inspired air. That inspired air pressure has to take up some portion of this 760. So that's why I'm subtracting 47 from the barometric pressure. We're left with 713. So in our airways, how much oxygen in millimeters of mercury is in our airways? Well, it's 21% of what? The 713 number, not just 760.
So we have to account for what the body does to the inhaled air?
Correct.
Which
correct.
is,
Which-
humidity and heat, which changes the
Correct.
pressure to
Which
700.
moisturizes the inspired gas. So that moisture has to take up some of that 760. Where we're going with this, and again, I emphasize the word airways. I may have accidentally slipped out alveoli. I didn't mean to slip out alveoli. I'm saying airways. Because think about, and we're not there yet, we're getting there, but I'll go ahead and just allude to it. When 760 is out here, I breathe it in the airways, now it's about 150. Where's the gas going next? The alveoli. What gas do you think is in the alveoli that we will have to exhale? Guess what? Now I'm going to have to figure out carbon dioxide is going to need to take up some space in that alveoli. So this number is not the number that reaches our alveoli, because again, the alveoli are going to have some carbon dioxide. But we're not there yet. We're not there to solve it, so don't worry about that. But at some point, this number that's in our airways is going to be even less by the time it gets into our alveolus. Because again, inside our alveolus, there's going to be some carbon dioxide taking up residence, being ready to be exhaled. Okay? All right, so 160, again, millimeters of mercury, partial pressure of oxygen in the room. By the time it reaches our airways, because of heat humidification, it's now about 150 millimeters of mercury, oxygen. All right. Totally confused now?
Yes.
Fantastic. I can sleep well tonight. Disappointing. It takes time. We'll talk about it on more than one occasion, obviously. But let's continue. Let's continue. I got a couple more questions for you guys that I didn't share on the PowerPoint. All right, so knowing this, and this represents you and I breathing right now, how much oxygen in millimeters of mercury is in our airways, because you know you and I are breathing how much oxygen? 21%. So that's what's available in our airways for you and I, normal people, to breathe in. But what about our sick patient in the hospital? That we connect them to oxygen. I know some of you guys are talking about oxygen devices and things like that. So here's my question. You can snap a picture of this if you want to. What would be the partial pressure of oxygen in the airways if we put you, or we put our patient, on 50% oxygen? I should tell you, just hold off because I got the math on the screen here, so if you want a complete picture instead of taking multiples.
We have that.
You do have this one? Okay. Do you have the answer too?
No, we don't have that.
Okay. Sorry. Well, then maybe you want to take a picture when I get to the answer. All right. But how do I figure this out? What am I gonna calculate? On the previous slide again on room air, what did we do? Room air times 713. What am I gonna do here? 50%. 0.5 times.
Oh, is it ready?
It's not 713?
In the airways.
Yeah.
I'm gonna do the same thing. Some of you guys just said it, right? I'm gonna do the same thing I did previously, but instead of multiplying it by you and I, because we're breathing what? Room air, 21%, I put this patient on 50% oxygen. So now they're getting 50% of the 713. Anybody quick with a calculator? Or are you just gonna assume I did the math right? Can't always trust me. I may do this late at night or early in the morning and hit the wrong button on the calculator. And I find out when I say an answer and I show the answer and people go, that's not right, I got something different. 356.5. Okay, where did that number come from? That is 50%, because we were on 50% oxygen. That is 50% of the 713 number. I get out of the way. So when you think about, well, we put somebody on oxygen because their body wasn't receiving enough oxygen. Now we're seeing this is how much oxygen we give them 50%. This is exactly how much oxygen we made available to their airways, which hopefully that increases the amount of oxygen in their body. Even with disease and illness, it's going to increase the amount of oxygen inside their body. Everybody okay with the math part? Where that number come from? So what do you think I'm going to do on the test? I'm going to change the FiO2, right? I'm going to change the oxygen concentration to 28%.
I just got a question, would you ever add the percentages, like if they were breathing room air and oxygen?
Well, doesn't room air have oxygen in it? Yeah.
Never mind.
No, okay, that's good. All right, so now we put somebody on something a little bit less, only 28%. They're on a 2-liter nasal cannula. 28%. How much oxygen is going to be available in their airways? So 28% of my 713 number. Only thing changing with these calculations is what? Really the FiO2, the oxygen concentration, oxygen percentage. What does it come out to be? 200? You guys are rounding up. So yeah, it is 200. So 199.64 millimeters of mercury. All right? You want to snap a picture of that just to make sure you can follow along with the math when you're looking at this later.
So when you ask it on the test, when you ask us to solve it, can we round up and you'll still take it?
It's gonna be multiple choice. ain't it?
Knowing it's a multiple choice test, you know, if it was a right in, you give me 199.64 millimeters of mercury, that's correct. You tell me 200 millimeters, that's correct in my book, in my opinion. But just on a multiple choice test, I can give you 199.6, I could round up and call it 200.
You'd be real mean and put 199.6 and 200 as the same, no.
That'd be funny though, but no, I wouldn't. I wouldn't be that cruel.
He'd probably break the computer because it'd be like, which one?
Right, everybody okay with this? Okay, one more, and then we'll move on. All right, we put someone on 100% oxygen. Uh-oh. So now we're giving them 100% O2. It's a code situation. Somebody go grab the crash cart. Let's go and get ready to intubate. Have them on 100% oxygen. Okay. Well, if you had to sit there and just think in your head, are they going to be receiving more partial pressure of oxygen in their airways now than they were on previous questions when they were on 50% or 28%? Hopefully you say yes, because yeah, we're giving them 100% oxygen now. So how much is that again?
713.
Math is real easy on this one, right? So 1 times 713 is 713 millimeters of mercury. Right, so when we have that sick patient who, because of disease and illness, can't get enough oxygen to their body, we put them on supplemental oxygen. We're just bumping up what's available to them. And in some instances, we have to give a whole lot of oxygen. And in other instances, we don't have to give quite so much, just depending what we're trying to provide the patient.
And this is just in the conducting.
And this is just in the airways. Yeah, we have yet to get to what
Oh my
reaches the
God.
alveolus. That's gonna be the next step. You said it, Chad. That's right. That's right. This is we're slowly leading into that. And that part is on another day, not today. Okay? All right, let's switch gears. Minute ventilation. Minute ventilation. All right, by definition, this is defined as the volume of air entering or even leaving the lung each minute. Hence the term minute ventilation. Clinically, how we do it is we usually measure all their exhaled tidal volumes over a minute's time. So just hypothetically say, I'm measuring your exhaled tidal volume. The last breath, you exhaled 490 mLs. The breath after that, you exhaled 510 mLs. The third breath after that, you exhaled 500 mLs. I keep doing that. I keep measuring that over how much time? 1 full minute. Not 1 minute and 5 seconds, not 55 seconds, no, for 60 seconds, 1 full minute, we measure how much air. I could say we can measure inhaled, but generally speaking, it's easiest to measure in a patient's exhaled tidal volume. So we can measure exhaled tidal volume for a single breath, or I simply measure those volumes over 1 full minute. Now what's highlighted in yellow, this VE is the acronym for minute ventilation. The reason you see the E there is because typically we see exhaled. So I measure their exhaled tidal volumes for 1 full complete minute. Now in the textbook it gives you both options. It says it's typically reported either as liters or milliliters. I will tell you this right now, what you're going to find most often clinically is it being measured in liters. Liters. And we'll do both. I'll give you both examples, but I will share it with you. You will see.
Liters or liters?
Liters or liters, exactly. Sorry. Oh, so liters, or it could be reported in liters per minute. Okay, I'm sorry, liters per minute. Let me add another piece. It could even be possibly said as milliliters per minute, or just in milliliters. But what you're typically going to find, is it in liters, or liters per minute.
Is this sometimes called minute volume too?
No, that's a good question. This is not the same thing as minute volume. Minute volume is different. That's Wednesday's talk. That's Wednesday's talk. And then we'll compare what we learned today, minute ventilation, to minute volume that we'll talk about on Wednesday. See, it all starts adding to itself until we finally get to the climax or peninsula of the information.
So does that F symbolize the respiratory rate?
Yes, yes. So minute ventilation equals tidal volume, and I'm going to say specifically exhaled tidal volume times F, which stands for frequency. Don't make yourself more confused than you have to be. Frequency is the same thing as respiratory rate. But the abbreviation they always give it is that F for frequency. That's the same thing as respiratory rate. Now, Connor wants to spoil my surprise about alveolar ventilation, but minute ventilation does not specifically tell us the amount of ventilation that participates in gas exchange. What Connor's referencing, and don't worry, we'll get to it on Wednesday. What Connor was referencing with his question was the one that does. Okay? But minute ventilation does not tell us specifically volume that participated in gas exchange. All right, so I do have some questions. And I don't remember if I gave you this slide or not. I did, okay. I was being a nice guy. I probably didn't want to make you think you were getting off too early with giving you only 10 slides, and I took out all of these. All right, so, for example, we'll just use us right now. Our tidal volume is 500 mLs. We're breathing a very comfortable 12 times a minute. What is your minute ventilation. Okay, I hear 6 liters. 6,000 milliliters. Okay? Alright, so when you're doing this, you can take 500, multiply it by 12. Your answer would be in
6,000
milliliters, right? Or you can convert this right off the top to liters, which how do you do that? How do you convert 500 mLs to liters? You put a point right in front of the 5. 0.5 liters. Okay? What you're doing is moving the decimal place 3 times over. Alright, let's do the math. 500 mLs times the frequency, or 12 breaths a minute, equals 6,000 mLs per minute. That's a correct answer to this question. What is the minute ventilation when you're breathing this way? Or, if I put it in liters, it is 6 liters, or 6 liters per minute. But what did I say you're going to see most often used? The liters per minute. So with this math, make sure you can do this math. Tidal volume times the frequency, or tidal volume times their respiratory rate. That's going to give us minute ventilation. You're okay with this math, and you're wanting to snap a picture of it, Sorry, that's up there at the bottom. I'll say when they put these rooms together, they never asked me where that station should be kept. Once I walked in here, I'm like, but people sitting on that first row over there are not going to be able to see every single thing. They should have moved it over here to the side or something. Nobody asked me for my opinion. I just work. Yeah, there you go. I just work here. Yeah, I have no power over in this corner. That's probably why they put it there. Okay, everybody okay with the math? All right. I didn't give you this question, this slide. What didn't I give you? All right, so the question is, what if the tidal volume is 800 and the patient's frequency or respiratory rate is 8? Okay. So punch that in the calculator. Again, I typically would want to know this answer in liters. So I can make this 0.8, would make it liters. 0.8 times 8 is 6.4 liters. Okay, 6.4 liters. Everybody okay with that one? Where that math came from, how you got that number? My second question, what if the tidal volume is 400 and the frequency or respiratory rate is 16? How can it be the same thing? It's different numbers. Notice, in this example, the patient's tidal volume dropped by half, but their respiratory rate doubled. Okay? Same number. This is not the best, this is not the easiest example. Let's just say this is me and you right now. Comfortable, normal as can be. But we had disease, we had illness, we had severe muscle weakness, and now we can no longer do the amount we were capable of doing. So our tidal volume drops. What's the only way we can maintain the same minute ventilation? I would have to increase my respiratory rate. I have to increase my breathing to keep my minute ventilation the same. Okay? So how do you think our poor patient is who's very, very sick and has such a small tidal volume? No wonder why they are breathing so fast. They're trying to maintain their same minute ventilation. And of course we know you can only breathe so fast for so long before you physically are no longer able to, and now that's the situation where the patient is now coding cardiopulmonary arrest type situation, which obviously we don't want that to happen. All right, but yes, mathematically, 6.4, same number, same number.
You will always be proportional with the effort, with the amount that your, like, the tidal volume and the respiration will always have the same proportion. Like here, decrease by 50,
Here was
increasing.
Here was perfect because I wanted you to be able to see it.
But it's not always that same proportion, like.
It could be, to be fair, it could be. Again, my body's gonna try to do whatever it can to maintain my minute ventilation. And if it can't do it by maintaining my normal tidal volume, the only way it's gonna try to make up that difference is making me breathe faster. All right, I do have a few more examples here. So what if the tidal volume is 600 and the frequency is 10? Okay, the max is more simple. All right, 6 liters. Everybody okay where that number is coming from? 6 liters. Next question, what if the tidal volume is 500 and the frequency is 12? Also 6 liters. So tidal volume dropped a little bit and the respiratory rate picked up a little bit. And again, that's the body trying to maintain its same minute ventilation. Gotta love the math. Gotta love the math. I heard that. I don't like the math. I think I have one more. Don't I? Oh, no, I don't. Okay, so before I get to the next one, everybody okay with what we have here? All right.
What's that?
All right, so
What's that?
solve the minute ventilation worksheet.
Oh. Let's place the lowest gas grade up to the snow.
You wish. If I'm doing that, it's going to be something a whole lot harder than this.
Thank you. You're welcome.
Okay, so you'll find that this semester, we're going to have some calculations. There are going to be some formulas we're going to have to do. For most of them, good chunk of them, I like to do these things for us to work on together to make sure you're comfortable with the math, that you're understanding where the numbers are coming from. I am not going to collect this. This is not a grade. This could be a homework assignment or parts of it could be a homework assignment for in the future, but this is something I'm not collecting. This is not something I'm collecting from you. This is for you. We'll go over, make sure you all have the right answers. And I generally print plenty of a few extras anyways, if anybody has these. If not, I'm just gonna throw them away at the end of the day. So for the next 28 minutes, it's not gonna be that long. For the next few minutes, why don't you calculate, how many did I give you? 8? All right, I've given you 8 different